Assalamu alaikum wa rahmatullahi wa barakatuh. This is the second video in mechanical oscillation part 2. At the end of this part, you're going to be able to explain the free undamped oscillations of a torsion pendulum. It's good to remember from the previous video that the differential equation of the vertical elastic pendulum is x double prime plus omega 0 squared x equals to 0. The solution is x equals to x maximum sine or cosine omega 0 t plus phi. The proper pulsation or the proper angular frequency for the vertical elastic pendulum is given by omega 0 equals to the radical k over m, and its natural or proper period is 2 pi radical m over k. From the first lesson, we took that a torsion wire of torsion constant C possesses a torsion elastic potential energy given by half C theta squared. We are going to start with some prerequisites about rotation, since we are going to need them in our lesson. In rotation, we should remember the ideas of the moment of a force, the angular abscissa, and the time equations of motion. What about the moment of a force? The moment of a force is a physical quantity that measures the tendency of the force to rotate an object about a given axis. So suppose we have this rod, and given the axis of rotation delta, we apply the force F at a point on this rod, taking the positive sense of rotation clockwise. The moment of this force is given by plus or minus F times D, such that F is the magnitude of the force in Newton, D is the lever arm, which is the perpendicular distance between the axis of rotation and the line of action of the force. The moment is the moment of the force with respect to delta in Newton meter. Now, if the moment is positive, then F tends to turn the rod in the positive direction, where if it's negative, then F tends to turn it to the negative direction. But if this moment is 0, it means that F doesn't have a rotational effect. When this moment is 0, the moment of a force with respect to an axis of rotation is equal to 0 in two cases. First, when the line of action of the force passes through the axis of rotation. Second, if the line of action of the force is parallel to the axis of rotation. We have defined in the previous year the angular abscissa as theta, which is in radians. Then we found that the angular velocity is given as theta prime, which is the derivative of theta, the angular acceleration, which is the derivative of the angular velocity. Moreover, we said that we can integrate theta double prime and find theta prime, and also integrating theta prime to find theta. Defining the type of motion helps us in understanding this idea. Starting with the uniform rotational motion, we know that theta double prime is 0. Then integral of 0 is constant, and it is a not zero constant. Then the integration of such constant is given as theta prime t plus theta 0, which is the angular abscissa at t equals to 0. What about the uniformly varied rotational motion? Also, we know that theta double prime is a non-zero constant. The integration of this constant is given by theta double prime t plus theta prime 0, which is the angular velocity at t equals to 0. Finally, if we integrate theta prime, we will have half theta double prime t squared plus theta prime 0 t plus theta 0. We are done with the prerequisites. Let's start with the first idea, which is the moment of the restoring torsion couple. First, we're going to define the torsion wire. A torsion wire is an elastic wire which stores elastic potential energy when twisted from its end about its axis. For an example, this is a torsion pendulum, which is formed of a torsion wire. The upper end of this torsion wire is fixed to a support, and the lower end is connected to a rigid cube. The cube is rotated from its equilibrium position in the horizontal plane about a vertical axis passing through the torsion wire. During the rotation of the cube, the wire is twisted, and then it exerts a restoring force, which is the torsion couple, on the cube. The restoring force tends to oppose the deformation of the wire and brings the cube back to its equilibrium position. When the cube is rotated by an angle theta, the wire is twisted through the same angle. The moment of the restoring torsion couple is proportional to the angular displacement theta, and it is given by the moment equals to minus c theta, such that the moment m is the restoring moment exerted by the wire in Newton meter, c is the torsion constant of the wire, theta is the angular abscissa in radians. Note that the minus sign means that m tends to return the wire to its equilibrium position. This idea is the same as what we took in translation for the tension of the spring, which is also a restoring force. It was given as minus kx, where the minus also tends to return the spring to its equilibrium position. The torsion pendulum is a mechanical oscillator. To study its free and damped oscillatory motion, we are going to consider this torsion pendulum. If the torsion wire is twisted by an angle theta, the pendulum starts to oscillate between two extremum positions. The positive sense of rotation is taken clockwise. In this case, when the disc rotates in the positive direction, then its angular velocity is positive, while if it rotates in the negative direction, then its angular velocity will be negative. The equilibrium position is characterized by a zero angular abscissa, which is theta equals to 0. Let's start with the expression of the potential elastic energy. The system is taken as pendulum. The potential energy is given by half c theta squared, where the energy in joules, c in a Newton meter per radians, theta in radians. This expression is similar to that of the elastic potential energy of the spring, where the elastic potential energy is half kx squared. When the spring has a constant k, here the torsion wire has a constant c. There we have x as a displacement, here we have theta as the displacement. In the aim to study the motion, we should define the mechanical energy. Mechanical energy at an instant t of the oscillations is given as the kinetic energy, the gravitational potential energy, and the potential torsion energy. Taking the horizontal plane passing through the plane of the disk as the gravitational potential energy reference, then the gravitational potential energy is 0. Thus, the mechanical energy can be written as just half I theta prime squared plus half c theta squared. We should start with the differential equation of the motion to find its time equation. So method 1, mechanical energy. At instant t, we have mechanical energy as half I theta prime squared plus half c theta squared. What is the second step? Good. We know that the mechanical energy is constant because there is no non-conservative forces. So we can make derivative, and the derivative of the mechanical energy is 0. Thus, we can write it as half I 2 theta prime theta double prime and plus half c into 2 theta theta prime. But we know that theta prime equals to 0 is not our case of study, so I theta double prime plus c theta equals to 0 is the second order differential equation without second number in theta. The second method is the Newton's second law. We know that the system here is disk. What are the forces acting on it? Good. We have the weight, which is vertically downward, the tension, which is vertically upward, and the couple of torsion of wire of moment m, which is equal to minus c theta. You should remember Newton's second law in rotation from last year, which is the sum of moments equals to I theta double prime, which is similar to the Newton's second law in translation, but instead of F, we have the moment of the force, and instead of m, we have the moment of inertia I, and instead of acceleration, we are talking about the angular acceleration. Now, writing the moments of the forces that we have, we can find that the moment of the weight and the moment of tension are zeros, since they pass through the axis of rotation. So we have only minus c theta equals to I theta double prime. Finally, we can write theta double prime plus c over I theta equals to 0, and here also it is the second order differential equation. What is the general solution of this differential equation? This differential equation is of the form theta double prime plus omega 0 squared theta, which is for the simple harmonic motion. Then it has a solution either theta equals to a sine omega 0 t plus phi, or theta equals to a cosine omega 0 t plus phi, such that a omega 0 phi are constants. Theta maximum is always positive. Theta is a sinusoidal function since it depends on sine and in cosine. The characteristics of this motion are the proper pulsation, omega 0, which is equal to radical c over I. The proper period is 2 pi radical I over c, and the proper frequency is 1 over 2 pi radical c over I. Let's solve an application. A torsion pendulum is formed of homogeneous rod AB of length L, 50 centimeters, a mass m, 0.5 kilograms, and a vertical torsion wire of constant 0.02 with no mass. This rod is shifted by an angle theta equals to minus 0.15 radians from its equilibrium position, and it is released without initial speed. Given that the angular abscissa of the rod at instant t is theta and the algebraic value of its velocity is theta prime equals to d theta by dt, the gravitational potential energy is 0 at the horizontal plane passing through the center of the rod. The friction is negligible. The moment of inertia of the rod relative to the wire is 1 over 12 ml squared. I want you please to pause the video at each part and try to think of it and solve it alone. Write at time t the expression of the mechanical energy of the system as a function of theta prime, theta I, and c. The mechanical energy is given as the kinetic energy plus the potential torsional energy plus the potential gravitational energy. So because the center of mass is passing through the reference of the gravitational potential energy, here we have the mechanical energy is just half I theta prime squared plus half c theta squared. Establish the differential equation of motion. So we should make derivative. Good. Finally, excellent. So we have theta double prime plus c over I theta equals to 0. Deduce the nature of this motion of the rod and the value of the proper period. The differential equation is of the form theta double prime plus omega 0 squared theta equals to 0. This means that it is a simple harmonic motion. And by comparison, omega 0 squared equals to c over I, which means that the period t 0 equals to 2 pi over omega 0 equals to 2 pi radical I over c. Calculating I, which is 1 over 12 ml squared, the period is 6.4 seconds. The solution of the differential equation is of this form. Determine theta maximum and phi. The same steps that we used to do in previous videos. We have the solution. We try to find its derivative to find theta prime. Then at t equals to 0, theta 0 is minus 0.15 equals to theta maximum sine phi. Theta prime 0 equals to 0, which is theta maximum omega 0 cosine phi. Now we have two equations. We start with the second one. Why? Because cosine phi is 0 in two methods. Either if phi is minus pi over 2 or plus pi over 2. To know which one is correct, we go back to the first equation. Minus 0.15 equals to theta maximum sine phi. But we know that theta maximum is positive, then sine phi is the negative part and phi is minus pi over 2. Replace phi by the first equation. We can find that theta maximum is 0.15 radians. These are the main ideas that you are going to compare them with the other application in other videos. And this is the end of part 2. Thanks for watching.